So as we have been looking at previously, we were getting used to the idea of these trig function graphs, where we had our sine, which ended up following along our path where our endpoint was 2 pi, and our start point being 0, maximum of a 1, and a minimum of -1, where at our halfway point, we basically make two kind of loops for our wave. So halfway point is pi, and we have pi over 2 over here, and 3 pi over 4 over here. We had our cosine wave, which along the exact same set of a graph ended up starting actually at 1 and dipping in as such, where peaks end up at the 2 pi and pi mark. We then also look at the tangent graph, which was a little bit different because rather than having a particular -1 minimum or maximum, there was no minimum and no maximum, where instead we actually went from infinity. And so we came up until we hit infinity going negative as well as positively, and we couldn't actually hit the pi or 2 pi value. We always were just getting really close to it. So after seeing all these graphs and kind of just getting used to them, if you still haven't at this point, I definitely recommend taking some time to just look at them, look back at the previous video and or lesson, and just kind of really get used to how these look. Because now we're using some of our knowledge from before, and we're actually going to be altering it just slightly to work with this a little better. So what I mean by that is previously we have worked with graphs and we've altered them. We've changed them around. We've taken our regular graphs, say something like x squared, and we've moved them around so that they end up upside down, wider, and just overall change where they end up. We're going to be doing the same exact thing except with sine, cosine, and tangent. So to remember, our previous way of changing any of those functions is we had a function f of x. We changed the x value by subtracting an h. We changed the y value by adding a k. And then overall, we multiplied the function itself by some a value to change its size. That was our general formula for any function. Now, as I kind of show in the slides, there's one issue with that, where in most functions like this, we are able to remove the multiplication somehow. What I mean by that is, say we had, best example would be a square root of something like 2x plus 2. Now this is our function, and we want to find our a, h, and k value, as well as the actual function. So immediately we might take the assumption that, well, of course it must be the square root of x, because that's the only x value there. Or you might also think that it is the square root of 2x, because that is the value and we can't really change that. So if you believe that it was a square root of x, that is actually correct, because we can alter this. The way that square root works, and the way that most of the functions work, is that you can somehow simplify it so that you receive only an x value being changed, either x squared, x to the third, etc., etc., where there is no value altering it. There are some minor exceptions. but for the most part that is true. See, in this case, it's somewhat obvious that within this square root, we have a common factor between the 2x and the 2, and so we could set it aside like this, where so far it is still the exact same function. We just separated out the 2. And the way that square roots work is that anything being multiplied, you could separate out the square roots to be separate. And then we could see that the square root of 2 becomes our a value. And then we still have, in this case, remembering that we switched the sign to get the h value. So instead of being positive 1, we'll set that a is the square root of 2. H, you flip the sign, becomes negative 1. And then k is just 0. There is no k value. So in this case, we can separate them. We can do that to make it so that our function is actually the square root of x. Now you may notice I'm going a little bit faster on this because this is more of the preliminary look on what we're doing. This is stuff that we should already know at this point, and if not, definitely make sure to remind yourself from your notes and everything on this, or retake a look at what we were doing there, where just remember that a changes the size, and so either brings the most of the values closer to y or closer to the x-axis. H changes the left and right direction of the graph, and k changes the up and down movement of the graph. Now, when we get to some of these functions, like, in the slides I end up using sine, I want to just show that it does not matter which of the functions you use. The process and the math for it is exactly the same, just the graph starts out differently. So in this case, we're going to use cosine, and in cosine, let's say we have a multiplication of 2x. You can't get that 2 out. There isn't some fancy way of saying, well, obviously, if you take the 2 out, the function is cosine of x times 2. You can't actually do that. So we need a way of incorporating that multiplier to the x, and we have the formula y is equal to a times t of b times x minus h plus k. Now, a lot of variables probably just got thrown at you. Definitely look at the slides to see what each one is, but I'm going to do a quick rundown here as well. So the ones that you may notice right off the bat are the ones that are exactly the same. So a is to a. Now, when we actually work with the trigonometric functions, we call this an amplitude. This is just your size. This is exactly what what size would do for the other functions as well. Amplitude is just the name we call it here. Next, we still have the h. H is still our xy change. In this case, we call it a phase shift because we are shifting the phase of our wave. And so it's basically just saying that this is our phase or x value shift. We have our k value, which again is just changing where it starts and the y axis. So this is our y change. The ones that are new is this t. So the t actually stands in for the f. So t is just standing in for trigonometric function. So that is t of x standing in for a function. That's basically just saying whether you're using sine, cosine, or tangent. Now the final value that is actually being added into is b. b is that multiplier inside of the function. When you have your sine of 3 times x, or your cosine of 5 times x, that's the 3 and the 5. That's what b is. So we call that frequency. There are other names for it, but it changes the frequency of your final function, and so it either shortens everything together or makes it much, much longer. So now we're going to see this in action. Now, the best place to see this is honestly just go online, take out your graphing calculators, plug in some of these, and really kind of get an idea of what is happening to these functions. Because as much as I can sit here, draw them out, explain them, it'll give you a grasp, and for some of you it may just immediately click, but there's no substitution for just going on and playing around with some of the values, seeing what does what types of values actually change it how, and so that's probably the best way. But in this case, we're going to kind of take each one one by one, so that at the end you can just combine the different types of shifts to see what actually happens. So again, I mentioned we were going to be working with cosine, so up in the left hand corner I'm going to set up a bit of a reference. So this one's going to be somewhat crude, but for the most part this is going to work as a reference. So we've got our 4 marks where we have our n value of 2 pi, because we're just working around our entire circle one time. We've got the halfway point of pi. We've got our first mark of pi over 2. Now this would be your 180 degrees, your 90 degrees, and this would be the 270 degrees, which I will mark as the 3 pi over 4. You could always think of this as a quarter, a half, 3/4, and the whole. I believe that should actually be 3 pi over 2. There we go. And then we actually draw out how it looks, where we have a maximum value of 1 up at the top. We have 0 as our midpoint and a -1 as our minimum. So when we draw this out, we start off at 1, we cross over at 0 for pi radical 2, we go to -1 at pi, go back to 0 here, and then back to 1. And we get this kind of U shape going through. So that's going to stay there as kind of a reference as we end up changing our cosine of x. So the first change we're going to look at is all the way on the inside, that h value. So we're going to see, one, why we call it a phase shift rather than just x shift. And then we're also going to see, because the initial thing when you make a grid is you make the x-axis and the y-axis. So that's what we're going to look at first. So it could be anything, but for the most part, whenever you shift it over a phase, it's easiest to draw out when you do it in terms of pi. So that's the pi over 2, pi, 3 pi over 2. So I'm going to change this by a value of pi. So x plus pi. Now also to remember is that the value you see in the function, when it's positive, it actually goes left, and when it's negative, it goes right. And as a quick on the side, that's because our h value, you have to negate whatever value is there. So if we wanted to get our proper h value here, then we would negate this and get negative pi, and negative goes left. So then we draw out our graph where, again, we have our 4 points of reference being 2 pi, being 3 pi over 2, pi, and pi over 2. And let's see what happens. Just to also have our 1, our 0, and our negative 1. So since we're moving this to the left by pi, so whatever was at our pi value now is our origin point, now is our starting point. So our pi value here was set at -1, and so we could actually see that drastic change between our phase of the wave starting here, and then it just continues the exact same pattern it had. So you could actually see that at h being -pi, it's almost like it flipped it over. Now, to remember, these graphs are continuous. They continue on the left in the same pattern and to the right on the same pattern. So be careful about saying that it's flipped, because this is just a different section of that same graph. We could just see that this one is one of the more drastic changes versus our cosine of pi. And if we took a look, if we drew in the starting value here, this would actually come up to right there, and we could see that we moved this part of our graph past our 0 point. Now let's move on to our y value. So I'm going to see if I can't keep most of this, because it won't do to constantly be rewriting everything. We have pi over 2, the -1. Alright. So in this case, now we're going to look at cosine again, but we're going to have our cosine of x as per normal. Let's see if I can't separate this a bit nicely. So we're going to have our cosine of x, but now we're going to change the y value. So let's add 2. So when we add 2, we would still, so to remember about the k value for these functions is we still have the exact same value. So we start off by drawing out our original function, or as close as we can draw to it, and then we change the y value. So we take our midpoint, our 0 here, and we move it up 2, because for the k value, positive does mean up and negative does mean down. So what I mean by changing the y value is 0, add 2 to 0, that makes that 2. So our midpoint is now 2. So now we go 1 above 2, which is 3, 1 below 2, which is 1, and if we can imagine on a graph, we would have the 0 point here, and the line as such showing our 4 points, and this line here would be non-existent. I'm going to keep the values for pi as they were, just for reference, but now we are up in the air, not along our origin point, and you could do the same thing for negative values as well, where you can almost think of it as an elevator, taking exactly the cosine of x shape, or alterations of based on your x, all the other values, and just shifting it up or down along the graph. Now I'm going to have to redraw the graph. But now let's move on to the final value that we would have, that we would recognize that outside multiplier, what we would call the amplitude or the size change. So let's make this one 3. 3 times cosine of x. Now again, we have the standard cosine of x, so we're going to be keeping the shape where we're going to have this between 0 and 2 pi. This alteration of the amplitude, though, changes how high and how low the value goes. So since we're not changing the y value, there's no plus k here, we're still starting at 0. But instead, that 3 becomes our maximum point. So here, where normally we would start at 1 at the very top here, this actually now becomes 3, and our minimum point becomes -3. So we still have that shape of starting at our maximum, and at each of the 4 points, 1, 2, 3, and 4, we cross the 0 at the first point, go to the maximum at the second, cross at the third, and maximum on the fourth. Just like here, but you could see it's larger. We could also make it smaller by multiplying by a third. And so rather than going to 1 like we normally would, we would start everything at a third, or wherever that would be. So when we combine all of these, we can get various locations for this wave. The one thing that has always stayed constant in this is the frequency. From peak to peak, no matter what we've changed, we've always held the consistency that from one peak to the other peak is 2 pi. And you could roll it back and see that every single one has kept up that you need 4 dashes to go from one peak to the other. Even if we move it to the left, we would still need 4 dashes to go from one peak to the other. This b value changes that. So there is a small little thing to remember about it, and that's that you don't take the value here as is to change its frequency. You actually need to take this value and take 2 pi divided by this value to get the proper frequency, to get how much it actually changes between it. And so one of the easiest ways to see this is I'm going to have a nice long graph going across with all of our values as per normal, where we have 2 pi, we have 3 pi over 2, we have pi, and we have pi over 2. 1, -1, 0. Now we're not going to change the amplitude, we're not going to change the xy value, we're only going to change its frequency. So the standard cosine graph is more or less like this. So that's what we have there. Maximum of 1, minimum of -1, and the peaks are where they're supposed to be. What if I decide to multiply the inside by 2x? Well, like I said, we take whatever b value is there, and we take 2 pi and divide it by that. and that becomes the frequency. Now, I had mentioned before that the distance from one peak to the other is 2 pi. And even following this formula, you can kind of see that, because normally there is an invisible 1 next to that x, and anything divided by 1 is that number. So that's why if this was 1, this would end up as 2 pi. But if we have 2, our frequency now becomes pi. What does that mean? That means that from our starting value, it should only take the distance to pi to finish everything. So from peak to peak, we should start our peak here and end our peak there. So we need to draw all of this within that space alone. So at our halfway point, like we would at 2 pi, half being pi, is where we have our minimum. So we would cross somewhere in the middle here and then do that. That is cosine of 2x. So it squishes it in because we are multiplying by a whole number. Now, what if we decided to multiply cosine the x on the inside by a fraction? Well, let's take a look at what cosine of x over 2 looks like. When you're dividing by 2, you would take the 2 pi divided by 1/2, and to remember, when dividing by a fraction, it is the same as taking its reciprocal. So it's the same as multiplying 2 pi by 2 over 1, which is just 2, and that equals 4 pi. So that means that this entire wave should take 4 pi distance to complete. So that actually widens it. So half of 4 pi would be 2 pi, because 4 pi divided by 2 is 2 pi. So that is where our minimum peak would be. Our starting peak would still be 1, and so we would cross about here, hit the minimum there, and then we would continue on until we hit 4 pi. So in this case, amplitude is the one difference that we really took a look at. And you can kind of see what it changes between here, because normally with graphs, we have a final endpoint which typically goes to negative infinity or infinity, and two endpoints at both ends. In this case, our endpoints shift infinitely, so we need a way to show it getting closer or farther apart. Hopefully these visuals kind of helped actually drawing through them. Again, I very much urge you guys to take a look just on the calculator and really just kind of see these changes. Add in different values, see where they end up, what actually happens to them, because this is a very kind of hands-on section. If this was clear to you, or especially extremely clear to you, then excellent. All you're really looking for is finding the values given within one of these functions. If not, absolutely plug the homework into a calculator and see the change for yourself. Actually see, best way to do it is to have the original function as a reference. And I know Desmos does it so that you could actually change the colors of each one. So have one as a reference function, and then have the other as the change. And that will be your best bet for really seeing these changes. Do one at a time. Change the h value, change the k value, kind of like what we did here, except really see those changes. I hope you're all doing well. Stay safe and healthy.